Good day, grade 12 learners. Welcome to today's mathematics lesson. My name is Sibusiso Shongwe, and this lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Right, today we will be looking at paper 1 revision. The focus would be on functions as well as differential calculus, because those are the two topics that contribute most of the marks in paper 1. Now also it's important to note that we first going to look at the overall structure of the paper. We check how much each topic weighs in a paper, and then we will check also some minimum targets that we can set out. Remember, as we are preparing now, we have a WhatsApp interactive number where you can actually ask us questions based on today's lesson. The number is 064 748 8913. 064 748 8913. Please use that number to ask questions, because you should have a lot of questions based on the fact that you are writing tomorrow. So we are just here to finalize your preparation for paper 1. Right, now first things first, we look at mark distribution and target setting. Obviously, if you check now for algebra would weigh 25 with a variance of 3 marks, which means that it will range between 22 and 28 marks. And the minimum marks that you should get to pass is 15 marks, just 15 marks on algebra. That's the minimum you can get. But I know you'll aim for way more than 15 marks. That's what we want from you. Right, in patterns and sequences, same weight as algebra, 22 to 28 marks, the range. And then the minimum marks you can aim at is 12 marks. That's just the minimum. Remember, you should always aim to get more than that. And then we have functions. That's what we'll focus on today. We have functions. If you check now the weighting there, it's 35 with a variance of 3, which means it can range between 32 to 38 marks. And what you need to target there would just be 15 for you to get just the minimum pass. And then we have finance, 15 with a variance of 3, which means that it would range between 12 and 18 marks. The minimum to aim for there is just the 5 marks. Remember, if you want a bachelor pass, then these are your minimum targeted marks if you want a bachelor, which means that you should aim for more than just the bare minimum in order for you to get 50% and above. Right, and then we have also differential calculus. That's if you see there, I put an asterisk. That's one other topic that would be focusing on today. Obviously, when we look at the weighting, we can see that it weighs 35 with a variance of 3, which means it can range between 32 to 38 marks. The minimum targeted marks there would be 10. But obviously you should aim for more than that, because you have your first principles there, you have your rules of differentiation there, you have your cubic graphs there, so you should aim for more. You have optimization concepts there, you should aim for more than 10 marks. 10 marks should just be the bare minimum. Right, we then also have probability and counting. Removing this asterisk there, probability and counting, 15 with a variance of 3, which means it can range between 12 to 18 marks. The minimum target there should be 10 marks. We know with probability, bulk of the work that would be examined would be from grade 10 and 11 probability. Your Venn diagrams, your tree diagrams, your contingency tables, your basic rules there, very, very important. Right. You can see that if you just get the bare minimum marks, then you'd be able to get 67 out of 150, because our paper is out of 150 for 3 hours. So you'd be able to get 67 out of 150, and for you to just get a minimum pass, you should get 45 marks. We should get 45 marks for just the bare minimum. Remember, I said to you, you should always aim for more. Should always aim for more. Normally say our subject is challenging, but it's not very difficult for one to pass. It's not as challenging as people think it might be. It is possible for you to pass. Yes, there will be challenges there and there, but there will also be enough questions for you to get your pass mark. Right, let's check now the distribution in terms of cognitive levels. That's where now we check our questions. They range between level 1 and level 4, where level 1 is normally routine questions, very easy questions, and level 4 is complex procedures, where you are required to then use your critical and analytical thinking skills. Now, if you check cognitive level 1, that would be knowledge type questions. They would always weigh 20% of the paper. They'll always weigh 20% of the paper, which means that you have enough lower order questions, or what we normally refer to as those low hanging fruits. You have enough of them for you to get a pass. Right, we then move to routine procedures. These are not necessarily difficult questions as well. These are routine questions that you've been doing in your classwork, in your homework, and in your class tests. These are just routine type questions, and they weigh between 52 to 53 marks. It's 35%. If you combine knowledge questions, which is 20%, together with the routine procedure questions, which is 35%, you can see that you already have 55% of the paper coming from those low-hanging fruits, coming from those accessible questions there. Now, obviously, we also have those complex procedures. Now, these ones, they involve complex calculations, higher order reasoning. There is often not an obvious route to the solution. Solution also may be based on real-world context. They require conceptual understanding. So, at times, you'll be required to integrate different topics. At times you'll be required to integrate different topics. Like for an example, in functions, they can ask you to calculate the angle, which means that you now infuse concept of inclination that you learned in paper 2 to integrate those concepts with the function so that you can be able to work out that angle. So that would be integrative type of questions. That would be representative of complex procedures there. Obviously, they will then take about 45 marks, which is 30% of the paper. And then we come to the higher order questions. That would be level 4 type questions, non-routine problems, which means that it's not necessarily something that you've seen before, something that requires you to dig deep into your creative and critical thinking skills. Problems are mainly unfamiliar. It's problems that you haven't seen from past papers before. They are mainly unfamiliar. They might require you to break the problem down into smaller parts, and they need at times interpreting and extrapolating of those solutions. You can use extra and interpolation there to solve those problems. They are based in unfamiliar context. That's very, very important. But they only make up 15% of the paper. It's only 15%. It's only between 22 to 23 marks, which means that bulk of the work would come from questions that you can access. Right, let's look at the information sheet. Obviously, the information sheet would be provided to you, and you should make full use of it. Now, obviously, you can check on the first sleeve of these information sheet. You can see these are formulas that we're going to be using in paper 1. These are formulas that are going to be useful in our paper 1. Right. On the next page, these are formulas that mostly work in paper 2. Remember, at times they can integrate those topics, but these are the formulas that mostly work in paper 2. But you know, with your information sheet, they will give you all the formulas, because at times they are aware that they can integrate topics. Right, obviously we then move on to the next one, which also is trigonometry, which is part and parcel of paper 2. And then from there, let us look at the examined concepts in functions. Now, the sketching of these functions. Sketching of a linear function, a quadratic function, a hyperbolic function, and an exponential function. You should know how to sketch all of them. Remember now, this one also has a different form. Y is equals to a into x plus p squared plus q. The turning point form should also be able to sketch all those functions. Now, determining the domain, the range, the asymptotes, turning point, intercepts, line of symmetry, and whether the function increases or decreases. Those are the basic characteristics of functions, and you should be able to determine them for all those algebraic functions that we've mentioned here. You should be able to take out the domain, the range, asymptotes were applicable, turning points were applicable, intercepts, line of symmetry were applicable. Now we should also be able to interpret all the functions together with their inverses. That's very, very important. Now, let's look at the summary of each and every function that we're going to look at in terms of our CAPS curriculum. Now, the standard form, we first start with the linear function. You can see the standard form is y is equals to mx plus c, or y is equals to ax plus q. And then we have that the shape depends on the value of m or the value of a. If m is positive, you have that this is an increasing function. This is an increasing function because when x increases, y also increases. And then you can see that now if there's a mistake here, it should be m less than 0. If m is less than 0 and a is less than 0, there's an error there. That's where now you get your decreasing function. That's where you get your decreasing function, which is telling you that when x increases, y decreases there. And then the domain of a straight line, x will take all real numbers from minus infinity to infinity, and the range as well, y will take all real numbers. Remember, domain represents the x values where the function is defined, and the range represents the y values where the function is permissible or the function is defined. Now, as far as the turning point is concerned, the straight line has no turning point, it has no asymptote, it has no axis of symmetry. So what's important is for you to know the shape, whether it's increasing function or a decreasing function. Should also know that this m here, in as much as it represents the shape, it also represents what? It represents the gradient of the function, which you can calculate using y2 minus y1 over x2 minus x1. That's if you are given two different points there. Right, moving on, we get to the hyperbolic function, the rectangular hyperbola. Now, the shape here also depends on the value of a. The value of a there, the parameter a tells us about the shape. The sign of that value, the sign of a. If a is positive, then we get that this is a decreasing function. You can see that now. If you are to look at these arms, these two arms, the one that is on the first quadrant and the one that is on the third quadrant, you will see that when x increases here, y is decreasing. Also with this one, when x increases, y is decreasing there. Normally, to explain the concept of increasing and decreasing function, I'll make use of that toy locomotive car and I'll place it on my graph and I'll move it from left to right. Like for an example, if I place my toy car here, from left to right of this function, you'll see that it will go down here, which means that now it is going downhill. So we are saying it's a decreasing function like that. If I were to place it also on this type of function, you see on this arm, you see that also it goes down. So you have that this is your decreasing function. So this function decreases from minus infinity to its asymptote, and also decreases above the asymptote to infinity. Now, the shape, you can see that we have the first, when A is positive, the terminal, the arm would be on the first and the third quadrant. But if A is less than 0, it would be on the second and fourth quadrant there. So that one should be an increasing function. Now, let's check what we mean by increasing function. When I use my toy locomotive that I said I normally use to explain increasing and decreasing, you can see that here from left to right, it is then going up. So we say that this is this type or this arm of the hyperbola represents an increasing function. Also, if you can place it here from left to right, you can see that it also goes up here. So which shows that now this hyperbola is an increasing function, or both the arms of this hyperbola represent an increasing function, which means when x increases, y also increases. Now, when we look at the domain, this graph, remember this graph has asymptotes, so it is defined only on all values excluding the asymptote, because remember the asymptote, we say that it's a line where the graph is not defined, so the graph cannot touch that line. It approaches the line but does not touch that line, so that is the asymptote. So the graph is not defined on the asymptote. That is why we are saying with the domain, the graph is defined for all real numbers except p, so except the value of what the asymptote. So the graph is not defined on the asymptote. The range as well, y is defined for all real numbers, but the graph is not defined on the asymptote. So we see that now our function is defined for all real numbers, just like the straight line, excluding the asymptote for the domain and also for the range. Now this graph has no turning point. It has no turning point. It has both the horizontal and vertical asymptote. The horizontal asymptote is x equal minus p. Remember, we are taking it from the equation. The equation, we have x plus p. So to get to the asymptote, we equate that to 0. So x is equals to minus p. So we get that from the equation. That's why we have that x is equals to minus p. And then y, we take that the value of q. That is why now y is equals to q, represents our horizontal asymptote. Now, to find the axis of symmetry, there are so many methods. Others would use y is equals to x plus c for the positive one, and y is equals to minus x plus c for the negative one, where this point y and x, y, this is a point where the asymptotes intersect, where the asymptotes here intersect, so that's how you can actually find your axis of symmetry. But there is another way, there's another method here which you can use, which you get straight from the equation. If you check, you have that the equation is y is equals to a over x plus p plus q. If you want the one with a positive gradient, then you're going to say this is y is equals to, you take this as it is like that, you get that this is x plus p and then plus q. If you want the one with a negative gradient, you go to your equation, you take all this again, but now you need to put a negative sign there so that now your gradient becomes negative. So these two give you the same answer as you'd get if you use this type of method there. So that's how you get your axis of symmetry. Remember, the line of symmetry is the line that cuts the graph into two equal halves. Right, that's enough as far as the summary of the hyperbola is concerned. We move on to the quadratic function or the parabola. Now we have two basic basic standard forms in this case. This one is called the turning point form. This is the turning point form because in this form we get that minus p maps q represents now the turning point. So if we are given the turning point, then normally the equation is written in the turning point form, and then we have this ax squared plus bx plus c, which is another standard form. That's what we use usually when we find our x-intercepts and we find our y-intercept. We know that there's a way of finding the turning point using that form as well. Now let's look at the shape. Obviously we can have that this is concave up. You can see that now it's concave up. We can also have it being concave down. Normally some teachers, we say it's a smiling face parabola as well as the frowning one. So it's a concave up as well as concave down there. Now the domain of a parabola would be x is defined for all real numbers. The graph is defined for all real values of x from minus infinity to infinity. But the range now depends on whether the graph is concave up or concave down. Suppose that you have this graph, for argument's sake, suppose that you have this graph which is concave down, like that. We know that this would represent now the turning point. This would represent the turning point now. So now this would be your axis of symmetry. Suppose that the turning point now is given by 2 and say 8. Suppose that it's given by 2 and 8. If you want to write your range there, it means that now you are going to make sure that the graph is going to be defined starting from here up until the turning point. So the graph is defined for y is less than or equals to 8. That is the range of this graph. It's defined for y is less than or equals to 8, or you can write it as from minus infinity to 8 included. That's where the graph is defined. So, but if this was a concave up parabola, say that this was then a point minus 1, a point 1 and minus 6, then this graph would have the range y greater or equals to minus 6, or you can write it as minus 6 included to infinity. That would be the range, because the range depends on whether the graph is concave down or concave up. If it is concave down, then it has a maximum turning point, which means that the graph is defined everywhere below the maximum. But if it is concave up, it has a minimum turning point, so the graph is defined anywhere from the turning point and above that particular turning point. So you can see here, we try to summarize that to say, if A is positive, then the graph is defined for y is greater than or equals to the y value of the turning point. That is why here in this form it says y greater or equals to q and y less or equals to q. That would be the range of this graph. It depends on whether the graph is concave up or concave down. The turning point, obviously, we normally use x is equals to minus b over 2a to find the x value of the turning point. And to find the y value, what do? We take whatever that we got for the axis of symmetry, we substitute it back to the original function. Hence, we get that this is a point minus b over 2a maps the function of minus b over 2a, because you substitute that original point back there. But now remember also, if you are using the turning point form, it should be minus p and q. That would represent the turning point. Now the axis of symmetry here would be x is equals to minus b over 2a in the form where you have the form y is equals to ax squared plus bx plus c. But if the form is different, if you have the form y is equals to a into x plus p squared plus q, to get to the axis of symmetry, you would equate x plus p to 0. Then you get that x is equals to minus p. That would give you the axis of symmetry for that particular graph, right? We move on to an exponential function now. An exponential function, remember, it can also be an increasing or a decreasing function. Your exponential function, let me go back to the parabola. The parabola here, I forgot to mention here that there is no asymptote. It has no asymptote. The parabola has no asymptote, good people. So moving on to the exponential graph. Remember now the parameters here are A, B, P, and Q. They are all very, very important. They are all very, very important. Now, B would tell us about the shape of the graph. Shape and position, very, very important. Shape and position, we get that from B as well as from A. B, if B is greater than 1, remember B cannot be equals to 0. Also, B cannot be equals to 1. So B should be greater than 1, or B should be trapped between 0 and 1, which is a fraction. Now, what happens here is that if B is greater than 1, then we get that this would be now our function like that here. And if A is positive, you get to see that the graph starts above the asymptote. So the value of A tells you whether you start above or below the asymptote. If A is positive, you will always start above the asymptote. But if A is negative, you will always start below the asymptote. You can see that these functions here, this function and that function, they start below the asymptote, but these two start above the asymptote because A was positive. But B now, B is going to tell you where to start with respect to the graph, because when you have exponential function, you know that it's either starting on the on this side, which is the negative x-axis, and then it intersects the y, and then it increases like that. Or at times, if it's an increasing function, at times if it's a decreasing function, then it will start on the positive x-axis like that, and it will decrease. So now what we get to see here is that this here, if you place your toy locomotive car, can see that it's going down, so it's a decreasing function. So the value of B tells you which side of the x-axis your graph starts from. So if your B is greater than 1, then it starts on the negative x-axis. Starts on the negative x-axis. But if B is trapped between 0 and 1, then it starts on the positive x-axis. Now let's check from these ones. You can see here B is greater than 1. The graph is starting here on the negative x-axis. You can also see here B is greater than 1. It is starting on the negative x-axis there. But A, remember, A tells you about whether you start above or below the asymptote. That's very, very important. Now the range, this graph is defined above the asymptote. If A is positive, then the graph should lie above the asymptote. That would be the range, because remember, the graph should not touch the asymptote. And also here, if A is negative, if it's below the asymptote, then you're going to say your range, the graph is defined below the asymptote. The asymptote that we only have a horizontal asymptote for an exponential function. There is no vertical asymptote. You only have a horizontal asymptote, and there's also no axis of symmetry for an exponential function. Right, I think we've said a mouthful as far as these functions are concerned. We spoke about those basic parameters. We're trying to summarize these functions. Now, let's get to problem solving. Now, most of the questions that I'll be doing with you are are questions where we interpret those functions. So we're going to interpret a lot of these functions. First, you can see that there's a sketched hyperbolic function which is defined on the first and the third quadrant, and then from there we are given a point on the function, or we are given a point where the two asymptotes intersect, and we are also given a point that lies on that particular function. And then the first question, they say write down the equations of the asymptotes of f. Now it's important here to note that we are given a point of intersection of those asymptotes. So we are given the value of x here and the value of y, which means we know what the asymptotes are. Remember, at times they would just write it this way. They would just write here y is equals to 3, and they would write x is equals to 2. And then if they ask you to write down the equations of the asymptote, it's easy for you to do so. But in this case, they've given us the point where the two asymptotes intersect. It means that we just have to take out the abscissa there, which is x is equals to 2 and y is equals to 3. These represents your equations of the asymptotes of this what you call of this hyperbolic function. So you just get that from the point where they intersect. Right, moving on, we want to now determine the equation of this function. Remember, in the previous question we worked out the asymptote, so we can just put the asymptotes here. We get that this is a over x minus 2 plus 3. One might ask, why am I putting x minus 2 there? Remember, x plus 2, or rather x is equals to 2 was the asymptote. So if I want to put this back into the function, then I would have that this is x minus 2 is equals to 0. That's what I have there on the equation. Alternatively, you can look at it this way to say, on the general equation, x plus p is equals to 0, which means x is equals to minus p. Already we know what x is. We know that our x is given by our x is given by 2. 2 is minus p, which means that p is equals to what? Negative 2. So you can just go there where you see p, you put negative 2, and where you see q there, you put 3. So I've just substituted the asymptotes there. Now I need to then find a point, because a point will assist me. Remember, this is y is equals to. A point will assist me now to work out the value of a, because for me to have this equation, I'm now in short of only one parameter a. So I'm going to substitute a point that lies on the graph. I'm going to substitute a point that lies on the graph. Reason being is that I know that if that point lies on the function, then it conforms to the equation of that particular function. So now what I'm going to do is I'm now going to substitute in my y is equals to a over x minus 2 plus 3. I'm going to substitute a point 1, 0. A point 1 and 0. Where x is 1 and y is 0. So where I see y, I put 0. And where I see x here, I'm going to put 1. 1 minus 2 plus 3. Transposing 3 here, I get that minus 3 is equals to a over minus 1. So a is equals to 3. Which means that, good people, our equation will be y is equals to 3 over x minus 2 plus 3. That's basically our equation there. Y is equals to 3 over x minus 2 plus 3. So that's the equation that governs this particular function. Now, moving right along, remember now we've worked out the equation. Y is equals to, we said it's 3 over x minus 2 plus 3. Now, they say write down the coordinates of D. Write down the coordinates of D, which means that we need to go to this particular function and check what point D represents. Now, if you look at point D represents the y-intercept of this hyperbola. It is where the hyperbola intersects the y-axis. So it is the y-intercept. And we know that point D is the y-intercept. It is the y-intercept of what? Of f. Now, how do we work out the y-intercept? Y-intercept y-intercept. To work it out, we put x to be equals to 0, or we let x to be equals to 0, which means that now we are going to have that this is y is equals to 3 over 0 minus 2 plus 3. This is y is equals to 3 over minus 2 plus 3. If you use your calculator and you input that on your calculator, you will get that y would be equals to 3 over 2. Y would be equals to 3 over 2, which means that the coordinate of D would be when x is 0, y is 3 over 2. When x is 0, y is 3 over 2. We simply looked at the graph and saw that D is the y-intercept. For us to get that y-intercept, we put x to be equals to 0. After doing that, then we find that y is 3 over 2, which means that the coordinates of D would be 0 and 3 over 2. Right, moving on with our work there, they're asking us now, is f an increasing or a decreasing function? Now, I'm going to start by rewriting the equation, 3 over x minus 2 plus 3, like that. Now, they're asking us whether it is an increasing or a decreasing function. Now, you would recall when I was doing the summary here, when I was busy with you here doing the summary of the hyperbolic function, we were able to talk about decreasing function and increasing function. So we are going back to that concept now. We are going back to that concept that now we are answering questions. We are answering questions. Is f an increasing or a decreasing function? I said to you, normally I'll put my toy car on each terminal ray there, on each arm of that parabola. You can see that now this toy locomotive is going down. So because it's going down, we say that it is decreasing. You can see also, even if you can place it here, remember it moves from the left hand side. It moves from the left hand side to the right hand side. So here you can see that now it is also going down. So we can conclude that this is a decreasing function. This is a decreasing function. But if they were to ask you why you are saying it's a decreasing function, then you would say when x increases, y decreases. That's how we define a decreasing function or an increasing function. Or we can also use what? We use the gradient of the tangent. If you are to put a tangent here, you can see that this tangent represents what? A decreasing gradient, a decreasing function. So we say that since the gradient of a tangent is negative, then this is a decreasing function. So you can explain a decreasing function using your gradient of a tangent or using the x value in comparison to the y value to say when x increases, y decreases. That is now a decreasing function. Now, we say that this is a decreasing function, but now the examiner decided to spice this up by saying, write down the values of x for which this function increases or decreases. Now, let's check the first arm. If you are to look at the first arm, you'll see that this graph moves from minus infinity, it is defined, up until here. Here it is not defined. So, we will say that this graph decreases for what? For x is less than 2. It decreases for all values of x that are this side. For all values of x that are this side, it is decreasing. But also it is decreasing for all values of x that are this side. So it is decreasing for x is less than 2 or for x is greater than 2. Where the graph is decreasing. It is decreasing on the left hand side of the asymptote as well as on the left hand side as well as on the right hand side of the asymptote. Alternatively, we can write this in our interval notation where we say the graph is increasing from minus infinity to 2, which we unify with what? 2 to positive infinity. That is where the graph is defined. It is defined from minus infinity to this point here, 2. That's the first one. Minus infinity to 2. also it is also defined here, or it is also decreasing here when you start this side, when you start from 2 to what now, to positive infinity. That's how we can write that down in our interval notation. Here we write that down in our inequality notation. That's where the graph is increasing, or that's where the graph is decreasing. Sorry, that's where the graph is decreasing. It decreases from minus infinity to 2, and from 2 to infinity. Right, moving right along. They want us to write down now the coordinates of the axis of symmetry. There's a mistake here. We're supposed to say the equation. Write down the equation of the axis of symmetry of f with a positive gradient. It is the equation, not the coordinate. So we want to write down the equation of the axis of symmetry of f with a positive gradient. Remember, I said we can do it this way. Remember, we have the equation y is equals to 3 over x minus 2 plus 3. To get 1 with a positive gradient, it means that we are interested in the one that is going to cut here. Divides the graph into 2. Remember, if we wanted the one with a negative gradient, it's this one. It also divides the graph into 2. But remember, I said to you, if you want the one with a positive gradient like that, we're then going to take this here. We're going to say y would be equals to x minus 2 plus 3. Then this is y is equals to x minus 2 plus 3. Y would be equals to x plus 1. So that would be the equation of the axis of symmetry with a positive gradient. That's how you simply get it from your equation there. Remember also, you can use the fact that y is equals to x plus c for the positive gradient one, where x and y represent this point here, the point where the asymptotes intersect, which means that if you are to use that method, then you're going to have 3 is equals to x is 2 plus c. Then you get that c is equals to 1. Therefore, you get that y is equals to x plus 1, which is obviously the same as what we got there. So it depends on you which method you want to use there. Right, we are moving on. Now, the last question, I think this should be the last question. It is on graphical transformations. It is on graphical transformations. So remember, it's important for you to know how to interpret these questions as well, to analyze transformations, your horizontal translation, vertical translation, and all that, vertical horizontal movement, your reflection about the x-axis, reflection about the y-axis. Those are all transformations that we can infuse in these functions. Now, it's important for you to be able to respond to questions on transformations. So an example of such question is this one. Let me rewrite the equation again here. Y is equals to 3 over x minus 2 plus 3. And then they are saying write down the domain of g if g of x is f of x minus 2. Now, I'm going to show you two methods that you can use to find this transformation. The first method, what I will do is I'll go to the original function, I'll find the domain of f, and then I'll check how f was transformed, then apply that transformation to ultimately get the domain of g. Now, let's look at f. F of x is equals to 3 over x minus 2 plus 3. What is the domain of f? Domain of f. It's all real numbers. This graph is defined for all real numbers except for the asymptote 2. That is the domain of f. Now, we are going to check what the transformation was from f to g. If you check here, the transformation was that we now have g is given as f of x minus 2, which means we are moving the graph of f by 2 units horizontally. So what is the movement? The movement here, or the translation The translation here is x minus 2 equals to 0, which means that x is equals to 2. So all the points are moved. Move f by 2 units to the right. Everything about f is shifted 2 units to the right, which means that its domain will also be shifted 2 units to the right. Therefore, the domain of G now, which they are interested in, the domain of G will now be x, an element of all real numbers, but x cannot be the 2 originally, and then it transformed by 2 units. So x cannot be equals to what? 4. So that would be the domain of G, because G is the graph of f that is moved by 2 units to the right. So what I did was I found the domain of the original function and then I transformed the domain. Alternatively, what we can do here is we can find the equation of G. We can find the equation of G, then get the domain from that equation. Now let's look at how to find G. G of x is equals to, they said it's f of x minus 2, which means that where I see x on the graph of f, I'm going to put x minus 2, because you see that now x is replaced by x minus 2. So this would be 3 over x minus 2 minus 2. You see, where I see x, I put x minus 2 plus 3. I can continue with it here. Can see that now G of x will then be equals to 3 over x minus 4 plus 3. This is the equation of G, which means that I can now find the domain of G. How am I going to find the domain of G? X takes all real numbers except for the asymptote, and the asymptote here is 4 from the equation. Can see that the asymptote is 4. So if you use this method, you still get the same answer as you got if you transformed the domain of the original function, rather than using the second method where we found the equation of G and then we worked out the domain from the equation. Right, we are moving on. Now you can see that we've exhausted our questions on the hyperbola. We now should work on the parabola, but we should try to do this as quickly as we can so that we can interpret more of these functions. Right, example 2, we are given s is minus 2 and 0 and t is 6 are the x-intercepts of the graph. So these are the x-intercepts of this graph, or defined by f of x is ax squared plus bx plus c, and r is the y-intercept. You are told that this one is the y-intercept. The straight line through r and t represents the graph of g of x, which is minus 2x plus d. Now determine the value of d. Determine the value of d. You can see that d lies on what? D is an unknown on the equation of the straight line. It is the y-intercept of the straight line. Now, what you can see here is that in order to get the value of, we can change this to y is minus 2x plus d. In order to get the value of d, I need y and I also need x. Which means that if I can find a point that lies on the straight line, then we will know that that particular point conforms to the equation y equals to minus 2x plus d. So now what I'm going to do is I'm going to check my straight line and check whether on my straight line I have a point that is given. Let me check there on your straight line. There is one point that is given, point T, which is a common point on the straight line as well as the parabola. So I can use that point to find the value of D. So I can say at a point T, 6 map 0. So now x is 6, y is 0. So where I see x, I can put now 6, and where I put y, I see y, I can put now 0. No, where I see x, I can put 6. Where I see y, I can put 0. So now you see that d is equals to what? D is equals to 12. So we've worked out the value of d, which means that this equation g of x is equals to minus 2x plus 12, because we've worked out that value of d. Right, we move on. Now they want us to find the equation, determine the equation of f. They want us to determine the equation of this parabola using whatever that is given to us. Now, remember, for you to get the equation of a parabola, you're going to check the form in which the parabola is given. If the parabola is given in x-intercept form, then you're going to use, if x-intercepts are given, then you're going to use y is equals to a into x minus x1, x minus x2, where x1 and x2 represent what now? The x-intercept. That's how you find the equation of a parabola if you are given the x-intercept. However, if you are given the turning point, then you use this form: y is equals to a into x plus p squared plus q, where minus p and q represents your turning point. So you can see the different forms. So it depends on what you are given. Now, if we check on the graph, we are given the two x-intercepts. So we are going to use the first form. So we will use the form y is equals to a into x minus x1, x minus x2. But it is important to note that here, you always need those x-intercepts and an additional point. So we will also need another point on the parabola. And in this case, you can see we have point R. Point R is the y-intercept of the parabola as well as the straight line. Since we have the straight line equation, remember we worked out that g of x is minus 2x plus 12, which means that it would be easy for us to find the y-intercept. By putting x to be 0, we can see that the point R is given by 0 and 12. We are finding that y-intercept because this point 0 and 12 represents the additional point that you need on the parabola. Remember, x1 and x2 represent your x-intercept. So what we're going to do is we're going to then substitute our x-intercept. The first one is minus 2. The second one is 6. So we get that y is equals to a into x plus 2, x minus 6. So from here you can see that the only unknown is y and x. If we can find the additional point by substituting y and x, then we'll be able to work out the unknown a. So what we're going to do is we're going to check a point on the line, on the parabola, which is a point 0 and 12. So where we see x, we put 0. Where we see y, we put 12. So 12 would be equals to a into 0 plus 2, 0 minus 6. So 12 is equals to minus 12a, because 0 plus 2 is 2 times minus 6, that's minus 12. So a is equals to negative 1. A is equals to negative 1, which means that therefore our y is equals to negative 1 into x plus 2, x minus 6. So what we can do is we can simplify this: negative into x squared minus 4x minus 12. Remember, when you FOIL this out, you'll get that this is x squared minus 6x plus 2x minus 12. That's where I got negative 4x. It's minus 6x plus 2x. I will continue here. Y would be equals to, I can then distribute the negative, minus x squared plus 4x plus 12. So that is the equation of this parabola. Y is equals to minus x squared plus 4x plus 12. So that's the equation of this parabola. We are moving on. Remember, they also said you should write it in this form. So that's very, very important. You should write it in that form. So that's why my solution here is written in the form that they demanded. Right. Moving along. If you see now the examiner is trying to then show you that, of course, the answer to the previous question was correct, because they are giving you the answer there to say if f of x is minus x squared plus 4x plus 12, calculate the coordinates of the turning point. Now, there's something I want to talk to you about here. You see, this examiner has given you the equation. The reason the examiner gives you the equation is that in this question, the examiner wants to allocate marks with accuracy. By so saying, I mean that the examiner wants you to get the exact answer as in the memo for you to get full marks. Now, if the examiner did not give you this equation, then you got, when you calculated here, you got a wrong answer. Then you use your wrong answer in this question to calculate the coordinates, to determine the coordinates of the turning point. Then the examiner, or the person who's going to be marking your script, was going to give you full marks for this question using consistent accuracy to say, since you got the previous question wrong, they are not going to penalize you for the second time here, so they'll give you full credit. But this examiner wanted to allocate these marks accurately, so as a result, he has given you the equation to say, if the equation is like this, then calculate the turning point. So obviously, what you basically do here is you say x is minus b over 2a to find the axis of symmetry, which means that now we're going to have minus into 4 over 2a is minus 1. So you can see that the axis of symmetry, x is equals to 2. That represents your axis of symmetry. Remember, you can also make use of the average at times. If you don't have the equation to find the axis of symmetry, you can use those x-intercepts, because the axis of symmetry is the midpoint between these 2 points. So you can find the axis of symmetry by adding the 2 points, x at s plus x at t divided by 2. This would be minus 2 plus 6 divided by 2. So x would be equals to 2, like that. Remember, you can also make use of calculus there. Now, in order to find the y value, you're then going to substitute 2 in the original equation. Minus 2 squared plus 4 into 2 plus 12. Now, this would simplify to 16. You use your calculator and get 16. Therefore, we get that the coordinates of the turning point would be given by 2 and 16. Remember, good people, this is important for you to be able to know how to use that form as well, because at times in these questions they will give you the axis of symmetry and they give you one x-intercept, and they want you to get the second x-intercept. So that's what the formula you should be using without being given the original equation or the original function, without being given that function there. So you should be able to use that particular midpoint formula for you to get the axis of symmetry. Right, moving on. For which values of k will f of x equal k have two distinct roots? So now we are infusing nature of roots to these functions. So nature of roots, remember, can be infused with any of the functions that you do. But now we are infusing the nature of roots with our quadratic function. So what we're going to do is we're going to check for which values of k will f of x equals k have two distinct roots. So now you can see that you are given f of x equals k, which means that your y is equals to k. So they are asking you for which values of y will you have two distinct roots. For which values of y will the line give you two distinct roots? So if you move a line y is equals to k, that would be the transformation line that you're going to move. A line y is equals to k. You want to get what? Two distinct roots. So you want this line to cut the graph on two different places. By distinct, they mean different, unique, on two unique or different places. Where can this line be? Now, if you check here, if you are to start off with your line here, if this is the line y is equals to k, remember here the turning point is 2 and 16. So this is a line y is equals to 16. How many times does the line y is equals to 16 touch the graph? It touches the graph only on the turning point. It touches the graph once, so it has one root. But if you are to move this line just down here, you can see now it starts touching twice, and it touches twice on two different places. So it has two distinct roots. As you continue moving this line down, you can see it touches twice. As you move it down further, it touches twice. As you move it down further as well, it touches twice. Remember, this graph here is telling you that it's going towards what? Negative infinity, and also this side towards negative infinity, which means as you move this line, continuously moving it down, it's going to be touching on two different points. So you have your two distinct roots. But now it does not only occur on one place, it occurs just below the turning point going down. So it occurs on the whole region that is below the turning point. On every region defined on the region below the turning point. So how do we define that? We would say y would be, it would occur for y is less than what? Y is less than 16. But remember, we are moving a line y is equals to k, which means that k, remember y is equals to k, which means that k should be less than 16, because just below the turning point, on that region below the turning point going down, you see that the line is touching on two different x values. So it has what we call two distinct roots. So that's when it has two distinct roots. So that's how you respond to that question there. Now up next, we are now working on these inequalities and graphs. They are saying f of x less than g of x. So here they are saying, remember, f of x is the y value of what? The parabola. They are saying it should be less than the y value of the straight line, because g of x is the straight line. So they are saying the y value of the parabola should be below the y value of the straight line. So they are telling you that now you need the parabola should be below the straight line. That's what they are saying. The parabola should be below the straight line. So we need to find that region where the parabola is below the straight line. Now, first things first here, in order to attempt this question, you first need to determine where the parabola. You should start by determining where they are equal, where the y value of the parabola is equal to the y value of the straight line. That is where now you're going to check from that particular point. That would be your critical value. Your critical value would be where they are equal, and then you're going to analyze from that critical value. So this is the point where the y value of the parabola is equal to the y value of the straight line. This is the point 0 and 12. This is another point where the y value of the parabola is equal to the y value of the straight line. This is a point 6 and 0. So now what I'm going to do is I'm going to draw vertical lines on my critical value. So I'm going to put a vertical line here and a vertical line there. Now remember, this line represents my critical value. The critical value here is 0 and the critical value here is 6. Critical value on my left hand side is 0. The critical value on my right hand side is 6. So I am now going to check on the left hand side of my vertical line. Check which graph is above. You can see this is G, this is F. You can see that the parabola here is below. On this region, on this space here, you can see that the parabola is below. The straight line is above. How do we define that region? We say x is less than 0. When x is less than 0 on that region. Now let us check in between the two, in between my two critical values, the two vertical lines. You can see that this is F and this is G. The parabola is now above and the straight line is below. That's not what I'm looking for. I'm looking for the parabola should be below. So that region does not have my answer. Now let's check on the right hand side of this line. You can see that here this is F, this is G, this is F. You can see now that the parabola is now below on this region. So it is also below when x is greater than 6. So that's where our parabola is below the straight line. Right, moving on. Another one. Now if you check, this one is a bit different. They are multiplying F times G. So it's a combination question. So where do you start? Where do you start here? If you check, it's F of x times G of x, which means it's the y of the parabola times the y of the straight line. They should be less than or equals to 0. So now the first thing that you're going to do, you're going to find where they are equals to 0. You're going to start by y value of the parabola times the y value of the straight line is equals to 0. So this represents y equals to 0, y of a parabola equals to 0, and y of a straight line equals to 0. That's where you start. So it means that you start on what? On the x-intercept, because this is the x-intercept where y is 0. This is also the x-intercept, which means that your critical values would be the x-intercept. So the first x-intercept is this one. The second x-intercept is that. So we draw also here our vertical line. So the vertical line here is -2. Also the vertical line here is 6. So we are drawing the vertical line where the graph is now or rather where we find our x-intercept. So now they want the product. If you check here, if they are looking for the product can be, if you have signs, if these signs are positive, then they'll give you a positive, and we want a negative, which means that you need the parabola positive and the straight line negative, or you need the straight line negative and the parabola positive. What does that mean? It means one graph should be above the x-axis and the other should be below the x-axis. One graph above, one graph below. So now we're going to check. Let's look at the straight line here. The straight line here is above, so it's going to be positive, and the parabola here is below, so I'm putting a negative here. The parabola here is above, so I'm putting the positive because it's above the x-axis. And then here it's below the x-axis, and then the straight line is above this region and it's below on this region. Now I'm going to make this easy by doing this, by putting my critical values -2 and 6. Obviously they are saying both of them should be included, so I shade that. Now in doing that, we are then going to say, okay, since we have these two here, what we can do is we can check on the left hand side, this side, we're going to check on the extreme left of my vertical line. You can see that the straight line F, G and F, you can see that G is positive, it's above the x-axis, but the straight line of the parabola F is below. So positive multiplied by negative, I get a negative here. And then in between G and F, in between the two vertical lines, you can see that G is positive, it's above the x-axis, and F is also positive above the x-axis. So if you multiply the two, you get a positive. Now check on the right hand side of the vertical line. You can see now that here on this region, F is negative and G is also negative. We are talking about this region here. You can see that they are both below. So negative multiplied by negative, you get a positive. Now they want, the answer that they are looking for is f of x times g of x is less than or equals to 0. So they want where the one is above and the other is below. So that would occur when x, this side, when x is less than or equals to -2. Like that, when x is less than or equals to -2. But remember, they said when the graphs, when the product is less than or equals to 0. So this is also part of the solution, or x is equals to 6. Remember, the points are included. So they want the graphs where both the graphs are, when one graph is above the x-axis and the other is below the x-axis, or they are both at the x-axis. So they are looking for one above, one below, or on the x-axis. So you can see that 6 is part of the solution because the graphs are on the x-axis. So that is why I included x is equals to 6 on that particular solution there. Right, good people, we are now moving on to inverses. I'm just going to rush quickly through these inverses. What we do now here is that we are going to start by explaining the concept of the inverse, and then from there we will answer a few questions on inverses. Now remember, on our inverses we first have y is equals to ax plus q. That is a straight line. We can define the inverse of that. This is the first one that we work with at this level. The second one is y is equals to a to the x. That's an exponential. The third one is y is equals to ax squared. That's a parabolic one. So these are the three type of functions that we're going to analyze inverses of. So it's the straight line, the exponential, and the parabola. Now, if we look at a simple example of a straight line, I'm just going to rush quickly through this. I want us to check the straight line. Suppose that you are given an equation y is equals to 2x plus 3, and we want to find, this is our f of x, we want to find the equation of the inverse. So basically what we do is we interchange x and y, because the graph and its inverse are symmetrical about the line y is equals to x. That's very, very important. So now what we're going to be doing here is that we interchange x and y. That is the first step when we want to find the inverse. So x would be equals to 2y plus 3, and then we make y the subject of the equation. We get that 2y is equals to x minus 3, then y is equals to half of x minus 3 over 2. So this will then represent f inverse x. This would be f inverse x. That would be half of x minus 3 over 2. That's how we can find the inverse of a straight line. But remember, it is also important to note that some of these functions are terminating functions. They do not have a domain that is minus infinity to infinity. At times they terminate. Now I want to show you something interesting here. Suppose that you are given y is equals to minus x minus 7, and you are required to find the inverse. This is f of x. You are required to find the inverse. If you interchange, you get that x is equals to minus y minus 7, and then if you make y the subject, y would be equals to minus x minus 7. If you check these two, they look the same. They are the same. So some linear functions are their own inverses. So that is very interesting to say that we get a linear function that is its own inverse. So this is only applicable for linear functions, right? I'm moving on now to quadratic functions. I'm going to use I'm moving on to exponential functions. I'm going to use an example. Y is equals to 2 to the x, and also y is equals to half to the x. Remember, we've spoken about this to say that if b here is a, if a is greater than 1, then we're going to have an increasing function. But here you can see that a is trapped between 0 and 1, which means that we're going to have now a decreasing function. Now we've sketched this before. You can then sketch the rough sketch of an increasing function like that, and what is important to note is that this intersects at 0 and 1, or it cuts the y-axis at 0 and 1. We can also have that a decreasing function like that. This also cuts at 0 and 1. So these are the exponential functions that we would study at this level. Now what happens is that, now remember, to get an inverse, we are saying the inverse is the reflection of a graph along the line y is equals to x. That is why we interchange values of x and y. So here, if we interchange x and y, we get that x is equals to 2 to the exponent of y, and this would take us to y is equals to the log to the base 2 of x. That is how you then write down the inverse of this particular function. In order to write the next one here, obviously we interchange. X would be half to the y, so y would be equals to the log to the base half of x. Remember, this can also be written as y is equals to minus the log to the base x, or the log to the base 2 of x, the log of x to the base of 2. So that is how you can interchange x and y and get the equation of the inverse, which is a logarithmic function. Obviously here, if we are to sketch the inverse, if we reflect this graph along this line, this is the graph that we are going to get. Now the point 0,1 becomes a point 1,0. If we reflect this one, we will see that now the reflection of this graph here would be a graph that looks like this. This point would be a point 1,0 like that. So that is how we are going to reflect a straight line. Now moving on, we get our parabolic function. This is how we reflect, I said a straight line, no, it's how we reflect our exponential graph in order to get our logarithmic graph. Now moving on to the next one, y is equals to ax squared. If I take an example, y is equals to x squared. If I draw this graph here, you can see that now this graph would be concave up like that, and if I were to invert this graph, I would have that this is x is equals to y squared, and if I make y the subject, y would be plus minus the square root of x. And remember, this will always hold when x is positive. Now if you were to draw the graph of this, you see that now the graph now would look this way. The graph would now look this way. Now if the graph looks that way, and we see that now this graph is no longer a one-to-one type of a relation. So what we do is we then going to check this original function. You can see if you subject that to a vertical line test, because at times here you are required to check whether the inverse is a function or not. So in order to check whether the inverse is a function, in this case you're going to subject it to the vertical line test. So if you put a vertical line here anywhere on this graph, you can see that it touches the graph on one point. So we say that the graph passes the vertical line test, or the vertical line test passes here, or the graph is a one-to-one type of a mapping. Now if you are to put a vertical line on this one, you will see that there are some areas of this graph where the graph touches the the vertical line touches the graph in more than one place. So in that case, we say that we have what we say that this graph here, or this relation, is not a function because it fails the vertical line test, or the vertical line test fails, or this is not a one-to-one mapping. It's a one-to-many mapping here, because this value of x, there's one value of x can correspond with two different values of y. So in order for us to then make this, a function, we need to restrict the domain of the original function. If we restrict the domain of the original function, then the the inverse will then be a function. Like for an example, if we are to restrict the domain of this, if we are to take only this portion of the original function, if we are to restrict the domain to x greater than or equals to 0, the range would be y greater than or equals to 0. You would see that we will get, if we want to invert that one, we are now going to get now the inverse now would be this way. Now you would get that now it passes the vertical line test. The inverse is now a function because we've restricted the domain of the original function. Right, that would be all as far as the explanation of the concept of inverses is concerned. Now we move on to this question. I'm only going to do one question on inverses. I'm going to work on only this one so that we can move on to calculus. Now, is f an increasing or a decreasing function? If you check here now, check the value of b. You can see that b, or you can say it's a. It's a is 1 over 3, which means that a is trapped between 0 and 1. So we will then say this is a decreasing function. It's a decreasing function. We can use different explanations. We can say it's because a is trapped between 0 and 1, or we can use this one. Remember when we explain increasing and decreasing function, I explained it in terms of values of x compared to values of y. We can say as x increases, y decreases. That is why we are saying it's a decreasing function. Now the second question, they want us to determine the equation of the inverse in that form. So our inverse, remember, it's f of x is equals to a third to the x. So it's y is equals to a third to the x. So the inverse, we interchange x and y first. So we have that our x would be equals to a third to the y, which means that now y would be the log of x to the base of a third. Remember, this can also be written in a different form. I showed you in the previous one. We can have that y is equals to, we write this this way, where we write 1 over 3, we use inverse law, it becomes 3 to the minus 1. So this would be 3 to the minus x, that's y. So if you interchange x and y, it's x is equals to 3 to the minus y, and then converting this to log form, this would be y is equals to, or minus y is equals to the log to the base 3 of x, and then if you divide by minus 1, you get that minus the log to the base 3 of x. So it can be written this way or that way. Right, moving on. Now write down the equation of the asymptote of f of x minus 5. Now you can see that they've transformed this graph, they've moved it 5 units down. So what was the asymptote of f? The asymptote of f was y equals to 0. The original function had an asymptote y equals to 0 because it couldn't touch the x axis. Now what is happening here? They've shifted the graph down. So therefore asymptote f of x minus 5, everything on the graph shifts down, so it will be y is equals to what? Y is equals to 5. That would be the equation of the asymptote. Now they want us to describe the transformation. If you recall from the previous question, we were able to talk to transformations. Now we want to do the same, but here now we want to describe the transformation in weights rather than using the transformation to get to the domain or the range. Now in order for us to describe the transformation, remember we converted this equation here, we converted it to y is equals to in log form. When we reflected this across y equals to x, it was a third, base a third to the x, or we say it's minus the log the base of 3 x, like that. So now if you are to compare, this is much easier to compare with that. It is much easier to compare with that. Now what happened first from f to g? First, in order for us to move and get a log, what did we do? We interchanged x and y. What type of transformation is that? We say that that is a translation along what? Or a reflection along the line y is equals to x. So first things first, f is reflected along line y equal x. That's what we did. And when we reflected x along line y equals to x, what did we get? We got minus the log to the base 3 of x. That's what we got when we reflected it along the line y is equals to x. But that's not the only thing that was done. You see here, this one has a negative, this one does not have a negative. What does that mean? It means that our y now became what? Negative y. Which means that f is then reflected across, or we can say along the x-axis. It is reflected along the x-axis. Why is that? We know when we reflect along the x-axis, y becomes what? Minus y. Which means that if you have an equation, y is equals to the log negative log to the base 3 of x. If you reflect along the x-axis, this would be minus y along x-axis. This would be minus y is equals to minus the log to the base 3 of x. Dividing by negative, we get that y is equals to the logarithm to the base 3 of x. So we get that it's now the same as what they wrote there. So they made two type of reflections in this case. Reflect along the y equals x and along the x-axis. Right. Good people, I'll stop here as far as functions are concerned. I want to touch on some basic principles of calculus now that would be examined tomorrow. That would be very, very important. Remember, wherever we did not reach, you guys you should go and do all these subtopics here. We're just going to remind you of these few concepts. Right, this I said I will not do. Right, differential calculus. Now let us look at what is examinable and what you should do as far as differential calculus is concerned. 1, you need to know the average gradient between 2 points. 2, the gradient of a tangent. 3, you need to know how to differentiate using rules of differentiation. Also, you need to know how to differentiate using first principles. You need to know how to find the equation of a tangent. You need to know how to apply the factor and remainder theorem when solving third-degree polynomials. You need to know how to sketch and interpret cubic functions. You also need to know how to deal with these optimization problems, which can be divided into word problems, shapes, graphs, motion, etc. Right, let's start with the average gradient. Now, we have some of the errors that you guys mostly perform when you work with average gradient as well as first principles. At times you make errors in terms of notation. Please, this are errors that are based on the fact that you don't at times use the formula sheet. Use the formula sheet to get the equation of the first principles. Right, and then sometimes you forget to put brackets when you do substitution. Sometimes you forget to remove the brackets correctly. Sometimes it's the language. We say we differentiate here. We are not deriving, we are differentiating. Right, let's look at this example here. Given f of x is 2x squared plus 4, determine the average gradient. That's the first question. The second question, we need to differentiate using first principles. The third question, we need to determine the gradient of a tangent to f. Right, let's start. First, we need to find the average gradient between those 2 points. By average gradient, they mean gradient between 2 points. That is average gradient. So that's the gradient you've been doing from your earlier grades. Now, what we're going to do here, we're going to find the corresponding values of y. We know that f of 2, we substitute 2 into that equation, we get 2 into 2 squared plus 4. Then we check that what will that give us? 2 into 2 squared plus 4, that's it should be giving you 8 plus 4, that should be 12. And we can also have 2 into 8. F of 8, 2 into 8 squared plus 4 is equals to, if we check that on our calculator, you can see that this gives us 132, which means that when x is 2, y is 12, and also when x is 8, y is 132. So we can then determine our gradient. Remember, gradient would be y2 minus y1 over x2 minus x1. So this would be 132 minus 12 over 8 minus 2. This would give you a gradient equals to 20. That's how you find the average gradient. Right, moving on. Determine f prime of x from first principles. From first principles, we know that f prime of x is equals to the limit as h tends to 0 of f of x plus h minus f of x over h. Now, the first thing that we do here, we compute f of x plus h. From the original, where you see x, you put x plus h. So this is 2 into x plus h squared plus 4. This would be 2 into x squared plus 2hx plus h squared plus 4. So this would be 2x squared plus 4hx plus 2h squared plus 4. So you've computed f of x plus h. Now we can go back and substitute. Therefore, f prime of x is equals to, this is the limit as h tends to 0, where you see f of x plus h, you're going to put what we've computed here. So this is 2x squared plus 4hx plus 2h squared plus 4, and then subtract the original function 2x squared plus 4 over h. Remember, good people, this is very, very important. There is no way in which you won't find this question in tomorrow's exam, and it will probably be for 5 marks. So you need to get all these 5 marks. So this is the limit as h tends to 0 of, if we simplify this, we see that the 2x squared and the 2x squared will give us 0. The 4 and the minus 4 here will give us 0. So we'll be left with 4hx plus 2h squared over h. We can continue with it here. So this would, f prime of x would be the limit as h tends to 0 of, now this would be, we are now going to take h out as a common factor, because you see the terms in the numerator, they contain h. So if we take h out as a common factor, this would be 4x plus 2h over h. So this would be the limit as h tends to 0 of 4x plus 2h. Now if h tends to 0, then we get that this is 4x plus 2 into 0. This is 4x. This is f prime of x. That is the derivative of f of x with respect to the first principle. Now I want you to look at C now. I want you to look at C. Please do C quickly for me for just 2 minutes. Try out C for 2 minutes and see what you obtain from that. Right, hello and welcome back. I hope you were able to work out that question very, very easy. They say here, hence determine the gradient of a tangent to f when x is equals to minus 3. Already we've worked out the gradient function, because what we got here is the gradient function. So this is a new function that tells us how the gradient changes as x changes. So you are told here that x is equals to minus 3. So we get that f prime of minus 3, this would be equals to 4 into minus 3. This would be minus 12 or negative 12. That would be negative 12. Therefore, the gradient is equals to negative 12, because you've already worked out the gradient function from first principles, and then from there they wanted the actual gradient or the instantaneous gradient when x is equals to minus 3. So we just substituted minus 3 on the gradient function. Right, I want to take you back, slightly back. There's somewhere where we made a mistake here. I'll talk to you quickly about that. Yeah, that's C here. This question here, C, we're writing down the equation of the asymptote. We're writing down the equation of the asymptote, and we wrote it as y is equals to 5. I wrote it as y is equals to 5. Remember, the graph was shifted down, so the equation of the asymptote should be y equals to minus 5. It's not y equals to 5, but it is y equals to minus 5, like that, because the graph was shifted down. So I made an error there, so I wanted us to correct that error before moving forward. Right, now we are now on the rules of differentiation. These are the common errors and misconceptions that you guys have. Notational errors, they come back again. The use of exponential laws, that's very, very important. At times we treat alpha as a variable. That's what we should not do. Alpha represents a constant there. Now let us look at this example where we should use rules of differentiation. Remember, in questions on calculus, they would start by asking you to differentiate using first principles, and then from there the next questions would be on, or the following questions would be on now rules of differentiation. So you'd have a few questions on rules, maybe 1 or 2 questions on rules of differentiation. So it's important that we do that as well. So now we are given f of x like that. So what I'm going to do is I'm going to first make sure that I distribute. I'll open these two brackets here because it was squared, and then when I multiply inside, I get that this is x. When I multiply this and that, I get 1. When I multiply this and that, I get 1. When I multiply these two, I'll get 1 over x. That's what happens when I multiply inside. When I void, now I simplify this, 1 plus 1, and then plus, I'll use the inverse law here because the x is on the denominator. So this would be x to the exponent of negative 1. Now that this is ready for differentiation, remember, for it to be ready for differentiation, you need to write it in a standard differentiable form, which means that you have no radicals. You remove those radicals, and you also remove the variables from the denominator so that they become numerators. That's very, very important. So now I can differentiate. If you check here, I did not write it as f prime of x because I was not differentiating. I was actually here, I was working out or I was simplifying this equation first before it can be differentiated. So it's important. You only write the notation when you start differentiating. So now this would be f prime of x would be equals to, I can still continue with my simplification here. I have a 1 plus 1. So x plus 2 plus x to the minus 1. I just wanted to simplify 1 plus 1 to give me 2. Now f prime of x here would be, when I differentiate x, I get 1. When I differentiate 2, I get 0. When I differentiate x to the exponent of minus 1, I get minus x to the exponent of minus 2. That's how I differentiate that. So this would be 1 minus 1 over x squared. I can leave it like that. Remember also here, it's enough. This is enough. You can leave it at that with negative exponents. It's still allowed. It's still allowed for you to leave it with negative exponents there. Very, very important. Now, moving on. Yeah, this is the next one. We're not going to do this one because of time. And moving on, this is the third one, which is a bit different from what we've been doing. Now, I want you to try this one out very quickly. It's a bit different from what we've been doing. I want you to try it out for just 2 minutes. For just 2, or let me give you 3 minutes. Please just try it out for a quick 3 minutes and see what you get here. I want to check what you're going to obtain here when you try to solve this one on your own. Just try it for 3 minutes. Your time starts now. Welcome back. I hope you were able to play around with that and you got it correct. I'm confident that you got it correct. Right. Let's look at it together. Now, if you check this one, y is not written as the subject of the equation. So y is not explicitly written. In that case, we need to try to make y the subject of the equation. So first things, what I'll do is I'll transpose the x cubed. So this would be x squared plus x cubed. That's what I did first. And then I'm going to divide uniformly throughout by x. Now y becomes x plus x squared. You see now y is explicitly written in terms of x, which means you can differentiate y in terms of x here, which means that I can now find dy dx, which is 1 plus 2x. So that's basically how you are supposed to work that out. Right. Let's move on. Now, let's look at the equation of a tangent. I want us to run quickly through determining the equation of a tangent. Now, remember, I said to you, when you differentiate, you find what we call the gradient function, which means that that particular equation that you get after differentiating, it represents the gradient. It is the function. It's a new function of a gradient, which means that whatever x value that you feed into that equation, you're going to get out the gradient. So the input is the x value, the output is the gradient. Remember, when you have y equals to or f of x equals to, you have now the function that is given in terms of x, where the input x gives you the value of y. But once you differentiate, you get what we call the gradient function, which is a new function that tells you about the gradient. It tells you how the gradient changes as x changes. Now, if you check here, determine the equation of a tangent. Now, remember, a tangent will be in this form, y equals to mx plus c. It has a gradient, which means you need a gradient and a point to find the equation of a tangent. Now, looking at this, you are given the equation of a function and you are given the point at x is equals to 2. First things first, we need to then work out the point of contact. How are you going to work out the point of contact? We are going to input 2 where we see x, so that we get the value of y when x is equals to 2. Because we know that if you have a tangent, the tangent, it should touch the function. So where it touches, we call that point the point of contact, which means that now to find the point of contact, we have that this is 2 squared minus 6 into 2 plus 5. Now what you're going to get here as the point of contact here would be minus 3. F of 2 is minus 3, which means that the point of contact would be 2 and minus 3. This is the point of contact. This would be the point of contact. Very, very important. So after finding the point of contact, then we can find the gradient of this graph. Now, remember what we said. We said when you differentiate, remember we have f of x is x squared minus 6x plus 5. When I differentiate this to get 2x minus 6, I just said to you, we find what we call the gradient function. So this is now called what? The gradient function. This is the new function that tells us how the gradient changes as x changes. So if I input the value 2, I get that this is 2 into 2 minus 6. This becomes minus 2. This becomes minus 2. Now, this minus 2 here that I get, let me continue with it here. This f prime of 2, which is minus 2, is my gradient. This is my gradient, is minus 2, because I've substituted the value of x on the gradient function, which means that what I get out when I fit the equation with x, I get the gradient out. Now I have the gradient and I need a point. Y minus y1 is m into x minus x1. We know that the gradient is minus 2. And the point, we're going to use the point of contact that we found. Point of contact is 2 minus 3. So if we are to substitute, we get y minus or y plus 3 is equals to m minus 2 into x minus 2, like that. So I substituted both the gradient and the point of contact. So we get that this is y is equals to minus 2x plus 4 minus 3. I distributed and transposed the 4. So y is equals to minus 2x plus 1. So this would be the equation of this particular tangent. It's very, very important to know how to determine that. You find the gradient and you find the point. Remember, to find the gradient, you need to differentiate to get the gradient function and then substitute the value of x to get the actual gradient, like that. Now, I'm moving on now to just the cubic function. I want to look at a basic cubic function with you, just a basic one. We have time for just one example to do here. So I'm going to look at just the basic cubic function. Now remember, the cubic function now, it will have at most 3 x-intercepts as well as 2 stationary points. But at times it can have 1 stationary point or no stationary point. When we have no stationary point, we're just going to have that point of inflection. So now, if it has 1 stationary point, that stationary point is called the stationary point of inflection. So it's very, very important. Also, with the one that is decreasing, you still have the same type of shapes there. It can have 2 stationary points, 1 stationary point, or no stationary point at all. Now, how do we sketch the cubic function? Step 1, we first determine the coordinates of the stationary point. Why do we normally start there? Because we want to know the basic shape, to say how many stationary points does it have. Number 2, we consider the sign and look at the general shape. We find the x and y intercept. We find the turning point, and we plot a smooth curve. Now, let's look at this basic questions. It's 2 questions here. The first one would demand of us to find these points D, E, and F, and then the next one would demand of us to find the turning point. We'll then stop there. Now, the graph of f of x is given by x cubed minus 4x squared minus 11x plus 30 is drawn below. A and B are the turning points of f. Determine the coordinates of D, E, and F. Now, if you check D, E, and F, you can see that these points represent what? The x-intercepts. So, in order for us to find the x-intercept, what do? We let y to be equals to 0, which means we would have x cubed minus 4x squared minus 11x plus 30 is equals to 0. That is the first step. We let y to be equals to 0 to find our x-intercepts. Now, we have a cubic polynomial. So the next step here would be to try and factorize. Now, if you look at this, we see that in order to factorize this, we need to use the factor theorem, which means we need to use trial and error to try out factors. I can try out factors starting from plus minus 1, plus minus 2, plus minus 3, and check which one will give me 0. Now, if I use 2 here, I will get that f of 2 is 2 cubed minus 4 into 2 squared minus 11 into 2 plus 30. This gives me 0, which means that x now minus 2 is a factor. Remember, you use trial and error to try and find out the one that would give you 0, because that would be your factor. So x minus 2 in this case is a factor. So if x minus 2 is a factor, you can use any of the 3 methods that you were taught. Either you were taught to factorize this by long division, by synthetic division, or by inspection. So we can just simply use our synthetic division. If we use our synthetic division here, we put a factor 2, and then we write down the coefficients of each term there. That is 1 minus 4 minus 11 plus 30. Those are the coefficients. Now, your synthetic division here would always start with a 0. So 1 plus 0, when we add 1 and 0, we get 1. 1 multiplied by 2, we get positive 2. Minus 4 plus 2, we get negative 2. Negative 2 times 2, we get negative 4. Minus 11 minus 4, we get negative 15. Negative 15 times 2, we get negative 30. And these two would give us 0. We know the last term there always should give us 0 if the point is a factor there. So now it means that we would have this as x minus 2 into x squared, because this is a coefficient of x squared, this is a coefficient of x, that's a constant, minus 2x minus 15. So moving on, we'll use this space, x minus 2, and then if we factorize this now, the factors of 15 are then 5 and 3 that we can use. 5, 5 here, and 3. The bigger one is negative. So that's what we have here. So x is equals to 2, or x equals to 5, or x equals to minus 3. These are the three x values that we have. So we are going to then trace them according to the function that is given. We can see that the one that is negative is d. So x at d is minus 3, and x at e is 2, x at f, that would be 5. Therefore, the coordinates of e would be 2 and 0. The coordinates of f would be 5 and 0. The coordinates of d would be minus 3 and 0. So you've worked out the coordinates of a, b, or rather of e, d, and f. So you used your factor theorem. That's very, very important. We use the factor theorem to do that. Now, next question, we want the coordinates of a and b. If we check now a and b there, when you look at these points, you can see that these represents what? The turning points. This represents what? The turning point. And we know for us to be able to determine the turning point, we need to differentiate and set our derivative to be 0, because at the turning point the gradient is 0. So I will first find the gradient function. This would be 3x squared minus 8x minus 11. That would be my gradient function. But we know at the turning point the gradient function is equals to 0, because the gradient at the turning point is 0, which means that 3x squared minus 8x minus 11 is equals to 0. If I factorize this, I get that this is 3x and x. We're going to look for the factors of 11 here. We're going to look for the factors of 11 that are going to actually give us the middle term, which is 8. So the factors that we're going to use here are 11 and 1. Minus 11 plus 1. Remember, if you cannot factorize this, just use your quadratic formula. So x is equals to 11 over 3, or x is equals to minus 1. You can see that 11 over 3 is the one that is positive, so that is x at b, and minus 1 is the x value that is negative, so that would be for a, the x at a. Now remember, in order for us to find the corresponding y values, we need to substitute f of 11 over 3 back into the original equation. We get 11 over 3 cubed minus 4 into 11 over 3 squared minus 11 into 11 over 3 plus 30. And this, when you put it in your calculator, it simplifies to minus 400 over 27. Also, when you use minus 1, this would be minus 1 cubed minus 4 into minus 1 squared minus 11 into minus 1 plus 30. And when you use minus 1, you punch that into your scientific calculator, and then this would give you 36, which means that the coordinates of, we said that 11 over 3 is associated with b. It's 11 over 3 and minus 400 over 27. And then for this point A, it would be negative 1 as well as 36. It will be negative 1 as well as 36. Remember, we differentiate, we set the derivative to be 0, and then we substitute back into the original function for us to be able to get the turning points. Right, good people, because of time, we will not be able to look at the other concept, but I trust and hope that in your preparations, as you finalize your preparations for paper 1, you touch on all those concepts. Remember, all the topics are important. Remember as well your target setting. Set those targets per topic and make sure that you then test yourself as to whether you are meeting those targets, because it's important to us that you do well in the subject mathematics so that it can open doors for you. I know you also are eager to do well in the subject, but in order for you to do well, you need to listen to your teachers. You need to also practice mathematics, because with maths it's about practice, practice, practice. You never stop practicing until you write those papers, and I have faith that you are going to do well in paper 1 tomorrow, and that you are going to take Gauteng back to where it belongs, in position 1. Thank you very much for watching. Please make sure you tune in again tomorrow for paper 2. Tomorrow we'll be doing paper 2. Please make sure you tune in for paper 2, and good luck. All of the best. Thank you and bye-bye.